Today is lecture number 5, chemistry for class 12, and we are starting the last applications of the aluminum diagrams is related to the metallurgy of aluminium. So today I am going to explain you about the metallurgy of aluminiums. That metallurgy is also working according to the aluminum diagram. So I am again going to draw a aluminum diagram. This one is T, that one is delta G, that is a 0 degree. So some lines are falling here. Generally in case of the magnesium, that one is the diagrams of the magnesium oxide, and that one is the diagrams of this aluminium Al2O3. So guys, see, the line of the aluminium oxide is lying below the 0. So it means the aluminium oxide has more delta G negative value. So it means those oxide, already we taught you, those oxide is belong below the line, this line. So these oxides are highly stable in nature. So it means that aluminium oxide is highly stable in nature. It is very difficult to break down this oxide with the help of heat. We require more amount of heat. Why? Because here the negative value for delta G is very high, like to be a magnesium. So here we are also applying a thermodynamic concept to explain how does the aluminium extract from its ore. Before starting the metallurgy of aluminium, I am just going to explain you about the thermodynamic concept of this aluminium metallurgy. Generally, you know, we require a proper reducing agent to remove an active metal from its ore. So here, proper reducing agents we are using. That reducing agent is coke. Second thing, we require a large amount of temperature. The temperature is another factor is helping to remove a particular metal from its ore. So what happened here? Here we know that Al2O3 is the more delta G negative value, so we require more temperature to remove the aluminium from its ore. So here we require more temperature as well as a more reducing agent. But the whole process is not take place in roasting or via calcination process. Here we require the ore not in a solid form, in a molten state. Or in the form of solution. So that's why the aluminium metallurgy is different from the another metallurgy, because here we are taking the ore in the molten stage or in a solution stage. And that's why in the previous method we are applying a concept delta G is equal to delta H minus T delta S. But guys, here we are applying a very important concept of related to the thermodynamics. This is delta G is equal to minus NFE, because this is a electrolytic reactions. In electrolytic reaction or electrolysis reactions, we are getting aluminium from its ore. So see guys, I'm just going to explain you about the delta G minus NEF. So what is the delta G? You know, the delta G naught is a Gibbs energy. Gibbs energy always in negative. These negative values helping us to identify the given reaction is spontaneous or a non-spontaneous. The next one, what is N? N is the number of electrons available, because here in this process in aluminium metallurgy, here electron is behaving like to be a reducing agent. Next, what is E? E is a standard electrode potential. And what about the F? F is a Faraday. So we need to convert the Faraday into Coulomb. So 1 Faraday is equal to 96,400 Coulomb. So we are just using this value if you are going to calculate the delta G value. So we are applying that type of the conditions of the thermodynamics. When this equation is only using and that conditions when the ore is available in their molten state or in a solution state. At that time we are applying this concept. So on the behalf of this we are going to abstract the aluminium from its ore. Because it's an electrolytic process, we require cathode as well as anode, and we require a more amount of solution of electrolyte, and this electrolyte contain more number of electron. You know very well about the electrolyte. So see next one. See guys, what is the use of this metallurgy? This metallurgy is useful to abstract aluminium from its ore, but except this, we are using that metallurgy for the abstraction of sodium, magnesium, aluminium, as well as another method is also sometimes chlorine is also. So these highly reactive metals, except in this one, these highly reactive metals are generally using to separate from its ore by the aluminium metallurgical method, and that metallurgy is take place by passing a electricity. So this is known as a electrolysis method. So that method is also known as the electrolysis method. So then we are going to discuss about the metallurgy of aluminium. In case of the metallurgy of aluminium, generally we are using first of all the concentration of ore. The first step is the main ore of the aluminium is bauxite or alumina. Bauxite contains few amount of moistures, but we are going to heat. We are getting Al2O3. This is known as the alumina. But according to aluminium diagram, it is a very stable oxide. So this oxide is giving you aluminium by the electrolysis process. So we are going to the concentration of ore by which process? Yes, by leaching process. We have already done. The leaching process is useful for the concentration of alumina ore. Okay, the concentration of aluminium. The second step is take place. All these steps take place inside a furnace. That process is known as the Hall-Héroult process. The metallurgy is known as the Hall-Héroult process. That process is useful to abstract aluminium from its ore, Al2O3. So here we are taking a furnace. This furnace, the outer part of this furnace is made up of the iron, and inner side, that layer, the blackish layer, is made up of the carbon, and this carbon is behaving like to be a cathode. Okay, it's behaving like to be a cathode and containing a negative charge. Inside this, we are taking a copper grid. With the help of this copper grid, we are passing the electricity, and with the help of this grid, a large amount of rod of carbon is available here, and this carbon is behaving like to be a anode. Inside this furnace, we also providing a way. This is outlet. This outlet is helpful to passing the large amount of aluminium when the aluminium is generating here, and they passing through this outlet. And this inside this furnace, that they contain a mixture of electrolyte. What is electrolyte? Main ore, जिसका आपको electrolysis करना है, जिससे aluminium को extract करना है, उसका ore यहाँ पे लेंगे. And this ore, we know this ore is not easily decomposable. So here we are adding K3AlF6. What is K3AlF6? K3AlF6 is known as the cryolite. And then we are also adding another substance, CaF2. CaF2 is calcium fluoride, but generally is known as the fluorspar. It is another ore of calcium. So here we are adding cryolite as well as fluorspar with Al2O3. What is the role of the cryolite and fluorspar? You know, the Al2O3 required more amount of heat to remove aluminium from them. So after adding cryolite and fluorspar, they help to minimize their energy. Those reactions take place, require more energy, but by adding these two substances, the energy level is reducing. First we required more energy, but after adding these two substances, we required very less energy. It means they helping to minimize the energy. Second, they help to decompose the aluminium oxide into their pure form. That is the role of cryolite and fluorspar. Sometimes 1 marks question is coming in your board examination. What is the role of cryolite as well as the fluorspar? and we are also adding some amount of coke, carbon. The layer of carbon is generating here. What is the role of this layer of coke or carbon in this process? This coke generating a layer, they behaving like to be a blanket and help to maintain the temperature inside. अगर इस process को खुला छोड़ेंगे तो large amount of heat is liberating outside. So this process is not able to maintain their heat. That's why we are adding coke, and coke is helpful to maintain their own energy. So see, that is the process. Then here that carbon electrode is behaving like to be a anode. The another carbon layer available inside the hot anode is behaving like to be a cathode. So this is the process. See, the reaction is take place inside the cathode as well as the anode. In case of the cathode, we know the cathode always have negative charge. So if the Al2O3 is decomposed, that is a reaction. Here the twice Al is removing and we are getting thrice CO also. Okay. So what happens in case of the cathode? The aluminium contain positive and oxygen contain negative charge. So the positive always moving toward this cathodes. So this one is Al. Al always have the +3 valency. So they require 3 electron and is converting into its neutral state. And this aluminium is heavier, so it settle down at the bottom of this tank and come outside with the help of this outlet. The second one is reaction is take place at anode. In case of the anodes, the carbon is available in their neutral phase. Here, the one oxygen is reacting with one coke and removing in the form of CO2. So one oxygen is reacting with carbon, so it's donating 2 electrons. The next one, the carbon is reacting with 2 oxygens and so in the next reactions, the carbon reacting with 2 oxygens and it's able to form CO2. One oxygen donating 2 electrons and 2 oxygen donating 4 electrons. So that reaction is take place at anode and that reaction is take place at cathode. That process is take place inside the hot anode process and you are getting the large amount of aluminium. So see, again we are going to these diagrams. So we are getting the aluminium and metal is heavier in nature, so it's settled down, and the nature of the electrolyte is lighter. So the electrolyte is floating above side and metal is settled down is below side. So metal is comes out with the help of this outlet. In this process, the per kilogram aluminium required required the more amount of carbon. Means to say, if the 1 kilogram aluminium is formed in this process, the every time the few amount of carbon is degenerated. So we need to remove this carbon and just place here a new carbon electrode. In this process, 99.9% aluminium is formed. So that is the process in which the large amount of aluminium is formed by this ore. That is the metallurgy of aluminium.